All right, our next team is team number 1. Team number 1, Team Twizzler, and their project is ThermoTrac, temperature RSS monitor. You may begin.
Good morning, I'm Daniel Gonzales of Team 1, and our project is the ThermoTrac. The other members of Team Twizzler are Tim Sack, Soyup, Hahn, Dave Hubbard, and Andrew Sack. There are a lot of companies out there that need a way to monitor the temperature of their temperature-sensitive products, particularly when they're in transit. There's also a high demand to track the position of some expensive products that certain establishments have. For example, there are over 7,500 hospitals in the U.S. alone that would find it necessary to monitor the position of their $1,000 machines. And the ThermoTrac is the solution to these problems. It is a low-power device that is capable of running off of 2 AA batteries for more than 3 years. It supports temperature monitoring or position tracking or both, depending on the user's preferences. Outside of the user's wireless network, it is going to take temperature readings and store it locally in memory. And once it enters the user's network, it's going to transmit the new reading along with all the old readings wirelessly. I'll now pass it on to Tim, who's going to talk about some of our hardware choices.
All right. So we chose a Type K thermocouple for our temperature probe. This is mainly because they're offered in a variety of wire lengths. So if we chose, for example, a thermistor, changing the wire length would change the value of the implant, so it messes with our values. And, we chose the GS1010. We didn't choose it because we require the game-pin GS1010. It's a low-power microprocessor with a separate built-in wireless microcontroller that handles all of the wireless communication for our device. And yeah, for our power source, we simply chose 2 AA lithium-ion batteries, pretty standard stuff. Motion detector is an ADXL 330, and we chose that because it's also very low power, and it runs the same 1.8 volts as the GS1010. And wireless transceiver, as I mentioned earlier, is integrated into the GS1010, so we're aware of that. We decided that the internal memory of the GS1010 was sufficient, and no external memory was needed, so all the data points are stored inside the GS1010. And again, for our analog digital converter, we use the ECE. Here's how our ThermoTrac system works. It spends most of its time here in sleep mode to save power, and then it'll wake up for one of 2 different reasons. The first reason being a temperature wake up, and when this happens, the temperature is recorded, and it checks to see if it's within a known wireless access, if it's within range of a known wireless access point. And if it's not, it will store the temperature locally, and then return to sleep mode to save power. If it is within a known wireless access range, it will send the unsent measurements, send the battery RSSI signals, and then go back to sleep. The second reason that it would wake up is for a motion wake up. And if it wakes up because of motion, it will either send the battery and RSSI signals if it's within range of an access point, or it will go back to sleep. And the reason that you would wake up because of motion is that when the device is standing still, you don't need to check its position very often because it's not moving. But once it starts moving, we want to be able to keep track of where it's going. So when it wakes up in motion, it'll start pulling the RSSI values more frequently, because the RSSI values, the signal strength values from the wireless network, are used to triangulate its location within a known wireless network. Which brings me to the wireless. So as I mentioned before, there's 2 main functions of the wireless. The first is simply to send our data readings to the server side to be stored. And the second is to determine its location. And the location is determined, like I said, by using as many RSSI values as it can find. And this is actually done on the server side, which is Ekahau's responsibility. We simply send them the RSSI values. And at the moment, we only have 1 RSSI value being sent, but we hope to expand that in the future. I'm going to pass it over to Soyup to go over the motion correction.
Our motion detection is comprised of 3 parts. A ADXL 330 accelerometer, which has 3 axes, a capacitor, 4 capacitors, and a 4-to-1 analog multiplexer. The primary part is the accelerometer, which measures which detects motion, and the capacitors are used to set the bandwidth from the accelerometer and also reduces noise. The reason why we have the analog mux is because GS1010 only has 2 ADC ports, one of which is already used by the temperature circuit. And thus, the 3 axes, 3 readings from the accelerometer is connected to each channels of the mux. This is our structure for the motion section. This is actually the accelerometer. This is the mux, and this is the pins from our GS1010. The 3 outputs from each of the accelerometer is connected to one of the 3 channels from the mux, which is then connected to the GS1010 pins shown here. The motion detection algorithm is actually pretty simple. It samples each of the axes from the group 500 times. It saves maximum and minimum values measured for each axis. It finds the difference between the maximum and minimum measured values. It compares this difference with the threshold value, and if this difference is greater than the threshold, then the motion is detected. Otherwise, it is not.
Thank you, Soyup. Now, I'm going to be discussing the temperature sensing portion of this device. For starters, it's based around, as I mentioned earlier, the thermocouple, which gives a length depth to measure temperature of whatever product it's actually attached to. In addition to having a thermocouple, we had considered using only a thermistor, but it didn't provide the depth, although we did end up needing a thermistor to account for the cold junction temperature, which is an issue that comes up when you have several different temperatures for several different materials joining. It creates a shortage in the actual voltage. Now, the temperature sensing has several other parts as well that are based around the thermocouple. Has a low power operation amplifier which will boost the signal so it can be discernible by the ADD converter. The ADD converter only goes up to about 1.8 volts and a change of 1 degree Celsius in the thermocouple reading would only be about a fraction of a millivolt. So any sort of voltage change in order for that 1 Celsius degree to be noticed has to be magnified quite a bit. In addition to that, the voltage on the thermocouple can go both positive and negative depending on what state it is. If it goes too low, it will go negative. In order to avoid a negative signal at our processor, in other words, in order to give it a signal that it can actually read, we had to attach a voltage boost to it, roughly 0.2, or rather, it's 0.2 millivolts, which we got from a 0.8 voltage converter and then decreased. In addition, there are resistors to create a non-inverting amplifier and capacitors just to hold a certain voltage level steady. Specifications needed to run in a 1.8 to 3.6 range. 3.6 coming from the battery, 1.8 coming from our voltage regulator on the GS1010. Like I said before, the voltage has to be positive, and the voltage also has to be discernible by the converter, and cannot exceed a voltage of 1.8 volts, which is the level that the ADD converter runs off of. So it's basically working a tightrope line, trying to get it high enough, but at the same time beneath that level. In order to determine the temperature according to the voltage created by the thermocouple, we use an algorithm based on the thermocouple voltage along with the thermistor temperatures I mentioned earlier. In addition, we had to take into account several components included in this device actually have a temperature dependence in themselves. So in software, we had to account for the fact that upon reaching a certain value of the thermistor temperature, that the voltages for the thermocouple would actually change slightly as well.